Hello students, welcome back, and let's go to number 3 of the derivative problems. And this was the problem. It was about, a combination of chain rule, quotient rule, and then the product rule, as a matter of fact. Let's see. Let's increase the font a little bit because we have a lot of small things here and there with those subscripts, superscripts, and fractions and so on. Okay. Let's calculate the derivative, and it is very clear that this is a chain rule to begin with because this is a composite function. We have big parentheses and then something, so let's apply the chain rule. Outside function is power function, so power comes out as coefficient. Nothing changes inside, of course, and then subtract 1 from the power and multiply the derivative of the inside. That's the structure of the chain rule. Any question here? Hopefully none. Okay, and then inside never changes, so let me just copy and paste the inside. No problem there. And then let's work out the derivative here. The derivative of the inside. Okay, all right, let's keep it like this and pause a little bit before going over to the next step. No, never mind. Let's go directly here. All right. Let's just do the derivative of the inside function. Okay, what's the derivative of the inside function? And you can clearly see that this is a quotient rule. You see, in the derivative problem, the rule is outside, in. Outside first and go in. If you do algebra, then if you have multiple parentheses or something, inside first, inside out, inside and then gradually go out. Calculus is backward, outside first. And outside we just did it. And the next largest structure is quotient rule, so let's do that. And what's the derivative structure of the quotient rule? The denominator square, which is really conspicuous, and then numerator we have quotient rule structure, u prime v minus u prime v minus uv prime. The derivative of the numerator here, and then the denominator, and then numerator, and then the derivative of the denominator. Yeah, that's the structure of the quotient rule. Common mistakes include sign mistakes. You have to have u prime v minus uv prime. Okay, let's fill everything in. And this parenthesis, derivative of the denominator, no big deal. Let's just copy and paste in. And then the derivative of the numerator, again, no big deal. Just copy and paste. You see, u prime v minus uv prime. That's the structure of the quotient rule. Okay, now let's take one extra step. Okay, what's the derivative of the numerator u prime? We have a product of two functions, which means this is going to be another product rule. Okay, this is going to be product rule. And how about this part? The derivative of denominator looks like this is pretty much straightforward. I don't have any special rule here. The derivative of the power function plus the derivative of the exponential function. Let's go ahead. Power comes out as coefficient, x to the, and then e minus first power, because I have to subtract 1 from the power. And exponential always stay the same. And that completes the derivative computation of the denominator. How about the numerator? That's going to be the product rule because we have product of two functions. Okay, let's go ahead and do that. The derivative of the numerator Okay, is everybody happy now? It's the product rule, u prime v plus uv prime form. u prime, the derivative of the power function, power comes out and subtract 1 from the power, and second function stay the same. First function stay the same and derivative of the second function, but the derivative of the second function happens to be the same as before because it's this exponential function. And that completes the problem. Okay, here we go. Personally, at first I intended this one as an easy problem, and then this one as moderate, and this one as harder problem. And that's why I arranged the problem like this. Turned out this was indeed easy. Very few students made any mistake here. And then this one, surprisingly, this turned out harder problem. Maybe there were some students, not just maybe, as a matter of fact, I graded this, and very typical mistake here was missing the outer function and starting from the derivative of cosine and the derivative of sine and missing those powers. Yeah, and then there were a lot of other things as well. Anyway, that turned out to be a problem. And then this, as a matter of fact, didn't turn out to be too much of a problem, as a matter of fact. And it was kind of moderately hard problem. It turned out that way. Let's see, more than half the students definitely, and maybe less than 3/4, about 2/3 of the students got this problem right, if I remember correctly. Even though this was a hard problem that combined, let's see, chain rule first, quotient rule second, and then the product rule. We had all those three coming up with confusing powers and exponential, but still, most of the students handled it okay. This, as a matter of fact, presented bigger problem. Okay, in case students also have trouble here in this semester as well, please remember whenever you have cosine to something power, sine to the something power, or tangent as well, outer function is the power function. Remember that. And tangent to the something is not that frequent, but sine, cosine, oh, those appear a lot because they're important in geometry and applications and in physics, optics, electromagnetism, you know what. So please expect a lot of sine cosine problems. Consequently, a lot of cosine to the certain power, sine to the certain power as well. Okay, so much for derivative computation problems. Let's go over to tangency problem. Now, tangency problems and the derivative computation problems go kind of hand in hand. I don't need bigger font here. Let's go back to normal. Now, please note that this function and that function are the same. So you can recycle the derivative computation you did here to this problem. All right, how do you handle the tangent line? This is what we want. Y equal to slope x minus x0 plus y0. This is the answer, the most desired answer, the type of answer I prefer the most. X0 value is given as e to the negative first power explicitly, and you have to find out what y0 is, and later on you have to find out what m is. So find out these two values, put those into the desired form, and you have the answer. Oh, by the way, some students may prefer this. Y minus y0 is equal to m x minus x0 in this form. And then we have points x0 comma y0 and then slope m. Especially the student who used Stewart's textbook, no, excuse me, not Stewart, Sullivan's textbook in college algebra, prefer this. And yes, I use Sullivan's textbook in college algebra when I teach as well. And there, in that course, this is the standard form for slope point equation of a line. Well, personally, I prefer this one because it's easier to graph this way over that way, and then there are some other reasons as well, linear approximation and so on and so forth. So let's use this form, and I hope everybody can clearly see the equivalence between one and the other. All you have to do is flip this to the other side, then we get the left-hand side. So that is the most desired form that we are looking for. And the first step is to find out y0, which is f of x0, and that is nothing more than, let's see, this is f of x, right? So, excuse me, I forgot x times. All I have to do is plug in e to the negative first power in place of all these, and we're going to get the answer. Let's see, what is log of e to the negative first power? Log and exponential cancel each other out because they're inverse functions. So this is actually e to the negative first power times negative 1, and then minus e to the negative first power, and consequently this is negative 2 e to the negative first power. This is the answer, but if you somehow prefer the decimal expression, I don't. I like precise expression better, but who knows, you may prefer decimal expression. In that case, you may want to do this. Punch in the calculator and then get, let's see, what is this? Okay, get this value. And if you use this value, I wouldn't mind. Personally, I'd prefer to use precise value, yes, but if you use this decimal, I wouldn't mind, it's okay. Anyway, we got y0. The blue part, we're done. Okay, we find out the slope, the red part. How do we do that? Well, first we have to find out the derivative. And that's something we did earlier. You see, we use product rule and then subtraction, so we ended up this kind of computation. And then let's recycle this result. That's log of x. Therefore, m is equal to, a little bit more space, log of e to the negative first power, because, you know, I'm plugging x0 value right here, this guy. And what is log of e to the negative first power? Log and exponential just cancel each other out because they're inverse functions. And that completes the red part. All right, we are ready. This is the equation of the tangent line we are looking for. Therefore, no, let me just plug those in. That's y0, and then okay, that's m. And that completes the problem. Slope point equation. Whoa, excuse me, one more thing. x0 is given as e to the negative first power, so I have to plug this one as well. Sometimes it happens. Okay, alright, sometimes fonts are broken up. So this is the answer that I prefer the most. And if you go over to my answer key here, which will be posted, you can see the graph as well. Now, if you prefer slope-intercept equation, you can break up the parentheses and get the final form like this as well if you want to. But personally, I prefer this form, slope point form, better than slope-intercept form. And then here's a graph. Okay, let's stop here and let's do the other problems in separate videos.